The concept of momentum originated from the Newton's second law. So in this lecture video, I will talk about the definition of momentum and why do we do that and how useful it is to use a momentum. So we already studied the Newton's laws, and we understand that Newton's second law says net force, which is written as sigma F or F net equals ma. And here m is the mass of an object. A is the acceleration of this object due to the net force. In principle, we can apply Newton's second law to solve any problems in kinematics. But sometimes there are some situations where it's very difficult to apply Newton's second law. It's either because of the force is a changing force and not a constant force, like in usual case. But also in some other cases, the process happens quickly, and it's usually hard to measure the force acting on the object. So that's why people think about how to apply this Newton's second law. How to change it so that we can get an equation that is applicable in some special cases, such as those I mentioned earlier. Okay, so let's start from this equation and let's see what we can do here. So we know from kinematics that the acceleration of an object is given by dv dt, the time derivative of the velocity. And let's separate this variable v and t, and let's put them in the two sides of the equation. F net dt equals m dv. Okay, and that's like a differential equation, and if I integrate on the two sides of this equation, and of course we put in some initial and final conditions which correspond to the lower bound and upper bound of these two integrals, then we will be able to perform a definite integral for both sides. Now to do that, I want to say here is initial condition, where we have the time instant ti, velocity vi, and the final condition, final velocity, final time instant t final, final velocity v final. And they correspond to, for the initial condition, lower bound, and for the final condition, upper bound of these two integrals. Okay, so let's put them right in. Ti, t final, vi, v final. All right, so now the left side, we're going to define this quantity. Okay, so now here's the definition. The left side here is defined as impulse. Net force integral over dt. You can also say net impulse, okay? Because just like a force correspond to each force, we can have each individual impulse, and this case here it would be impulse, okay? However, I'm going to just write down J here to represent the total impulse delivered to the object. And the right side, let's rewrite that a little bit. So let's assume that the mass here is a constant. So we can absorb the mass into the integral as the derivative. Okay? And then correspondingly, since I changed the variable here, I'm going to say vi here for the lower bound, and v final here. Okay? In fact, this equation, although we assume that mass is a constant, is a more general expression for this Newton's second law. It includes the case where the mass can change. One example of that is the rocket launch, right? So when the rocket goes further away from the Earth, the mass of the rocket decreases, and that's the case we're discussing here. So the m here is changing, right? So in this sense, this equation is more general. So we have a dmv here, okay? Now this mv is going to be called momentum. We use the symbol P to represent this mv product. It's called a momentum. Okay, now this integral, since mv is the variable, so we effectively integrate over 1. Integrand here is 1, and we go from initial to final, from pi to p final. Here now becomes dp. Okay, now that integral gives us p final minus p initial, which we call momentum change delta p. Delta p is called momentum change. Okay, so now let's go back to the Newton's second law. Now we have new symbols to represent Newton's second law. J for the left side equals delta p. And this equation also obtain a new name. It's called impulse momentum theorem. Okay, although we derived this equation from Newton's second law, but as I said at the beginning of this video, we can apply it to some other cases where the Newton's second law is really hard to apply. Okay, so that's why we give this an independent theorem. We give this new name. Okay. All right, so that's the momentum's concept and how we get Newton's second law to this new equation. Okay, now in order to apply this equation, it's very important that we know how to do calculation of the impulse and how to do calculation of the momentum change. Okay, so let's look at some examples. So now let's say I'm thinking about the impulse calculation. I'm going to study an object on this, let's say on the ground, and then there's a force acting on it. there's a pushing force. Let's call this F, okay, acting on it, push it around, and there's also a friction force, Fk, kinetic friction. Besides that, we also have this normal force acting on the object from this ground, and the direction is upward. There's also gravity, mg, acting on this object. Okay, so now let's say under these four forces, the object is moving with an acceleration a in the direction of the pushing force. Okay, now for this system, let's see how can we calculate the impulse. Suppose this object move from this initial position to this final position. And we also know final velocity. Let's call this V final, and initial velocity V initial. Okay, the object's mass, of course, is m. Okay, so these are just various initial conditions, and the object move from initial to final position. Let's say it moves time period delta t. Okay, so it takes time interval delta t to go from initial to final position due to all these forces. All right, so let's write down the net impulse. In fact, we can calculate each individual impulse. That way we'll have more practice. Okay, so let's see. Let's look at the each individual impulse, and then we will talk about the net impulse. So the impulse due to the force F is given by F dt integral, okay, from t initial to t final. Okay. Now in our case here, F is a constant force, so we can simply just move it out. dt, then we get F t final minus t initial, okay, which is delta t. All right, so that's the impulse due to force F. Now impulse due to the friction force Fk, let's see how we can calculate this. Fk dt ti t final. Okay. Now in principle, we can write down Fk equals mu k times n, and then times mg, etc. Okay, but right now let's just keep Fk in the equation, and Fk is a vector, right? So I forgot to mention that J here is a vector, and then Fk delta t. Now impulse due to the normal force equals normal force t, and of course we can write out n equals mg, right? But right now let me keep this normal force. That's the direction of the impulse, and times delta t. Lastly, gravity due to mg is mg delta t. All right, so now usually we define a coordinate system. So let's see. Let me draw this coordinate system first. So let's say that's x direction, that's y direction. Now the x-axis positive direction is along the force F, right? So that's this force F. Okay, so I'm gonna say now here we have F delta T, and F here represents the magnitude, and its direction is positive. So there's implicitly a positive sign here. Okay, now for Fk, it will be negative delta T, right? Since we introduced the positive x-axis, now is to the right, so Fk is negative. This vector is negative. For the normal force is positive, and gravity is negative. Okay, so we have all these impulse in various directions. Now the net impulse in the x direction, okay, so it's given by the impulse due to force F and impulse due to Fk. So we have positive F delta T minus Fk delta T, okay, and they give us this difference, force difference times delta T, and that is also the net force in the x direction. Now similarly, net force in net impulse in the y direction is given by positive normal force, negative gravity, delta T, and we have net force in the vertical direction times delta T. Okay, and we know the object's motion, right? So we know its equilibrium in the y direction. So these two forces must be equal. Therefore, we have a 0 here. And when we talk about the net impulse, right, the unit, SI unit is Newton second. So it's a derived unit from the force product with the time. Now in this direction, it's not the equilibrium, right? The object is accelerating, so we cannot get these to 0, but we can use Newton's second law, right? So let's see. Before we do that, let's write down the momentum. Momentum calculation. So we know the initial momentum is mass times initial velocity, and the final momentum is mass times the final velocity. So the momentum change, final momentum minus initial momentum, equals final velocity minus initial velocity. Okay, now specifically, if we use the coordinate system that we built in the previous slide, this slide here, so the x-axis represent that direction, and we have the understanding that these two velocities is along the x-axis. Okay. All right, so now let's see, can we get these to be equal to the equation here, the net force times the delta T, which give us the net torque, net impulse. So let's see, the net force in the x direction is ma in Newton's second law, right? and that times delta t. Okay, so let's see, what is that? The velocity we know from kinematics, right? So V final equals V initial plus acceleration times delta t. Okay, so that's one of the important one-dimensional kinematic equations that we studied before. The final velocity is related to initial velocity plus a acceleration times the time interval. Okay, so that's why I can continue with this calculation. I can use a delta t to replace the V final minus V initial. So that's exactly what we have here. We can see from Newton's second law, the net force is ma, and then if we replace it, we get exactly the same equation here. Okay, so therefore we can say the net impulse equals the momentum change. All right, so that's about the momentum definition and how we can use this new definition to reformulate the Newton's second law and then get a new law. Okay, and then next time we'll talk about how to apply this impulse momentum theorem to study some special cases where we have the either Newton's second law is hard to apply, or the force is a changing force, not a constant force. Okay, thanks for watching. In the previous video, we discussed how to define momentum and impulse so that we can get a new formulation of the Newton's second law. Now in this video, we'll talk about some cases where it's hard to apply Newton's second law, and application of the impulse momentum theorem is easier. Application of impulse momentum theorem. Now the first example I want to show you is the a tennis ball hitting the net of a racket. Tennis ball hitting, here is the racket. Let me draw a schematic picture to represent these two objects. Okay, so here's the net of the racket. Okay, now we have a tennis ball flies in with some initial velocity. Let's call this Vi before it hit the net. Okay, and while the ball is hitting the net, the net, of course, will have some deformation, right? So it will be pushed. The net will be pushed this way, and then here's the instant where we have the ball. The instant the ball is right on the net of the racket. Some deformation. Trying to draw some deformation of the net, the strings on the racket. Okay, all right, so let's talk about this process. Okay, and the the strings on the racket, of course, will apply a force on this tennis ball. Okay, so our focus is, or our system is, the tennis ball, and we are studying the force acting on the tennis ball. Okay, now in this case, we're going to neglect the gravity. Gravity, of course, is still there. It's just that compared to the force due to the net, right, acting on the ball, this force, the gravity is small, so we can neglect it. Okay. Now we know that the racket is like, their strings are like springs, right? So when you stretch them, they can give a reaction, so that there's a reacting force, right, on the tennis ball. So at this instant, let me draw the force, and that force is due to the string. Okay, kind of like spring force. Okay, and the more the deformation of the net of the racket, the larger the force. So this force, okay, so it's by the racket on the ball. Okay, changes with time. So it's a function of time. And this time can also be translated into the deformation of the string, right? The more deformation, the larger the force. So in principle, we can draw a picture for such a force. And it turns out to be this kind of diagram. So it's a bell-shaped curve that started from 0, representing the initial time instant when the tennis ball just touched the net, just touched the string, until the maximum deformation somewhere here, and then later on, when the string tries to return to its original length, the ball is being pushed backward, and then that will correspond to the other side of the bell shape. Okay, so the shape here is it's a bell-shaped force versus time diagram. Okay, so the force here you can see is changing all the time throughout the process. And here's the 0 force at the beginning. Okay, let's call this Ti, and that'll be the T final. Okay, and this line here, right, is right in the middle, represent maximum deformation or maximum distortion. Maximum distortion of the string. Okay, and here the force is max, so that's F max. Okay, so now we see in this case here, the force is changing with time, so it's very hard to apply Newton's second law, because we don't actually know exactly this kind of curve, right? The curve here. Okay, all right. So now think about the same problem, but from the momentum change point of view. So if I think about, let's say, afterward, here is again a racket, okay, and its net is going to, all these strings going to go back to the original shape. Okay, now you guessed what I'm going to say, right? So the tennis ball now flies out with a final velocity. Okay. Now in this case, these two velocities, they will correspond to this initial instant and final instant. Okay. So how about we think about the process here, not care about when we do not care about the intermediate process, this force changing with time process. Instead, we think about the initial and final momentum, and if we can figure that out, then we can say we solve the problem. Okay, so let's think about how about just talk about delta p, which is mass of the tennis ball times the velocity change, and then we get this final velocity from initial velocity plus delta p over m. So I simply just rearrange these m times vi term, rearrange it to the left side, and then it will be added up. It has summation with delta p, and then we divide by m. Okay, and then we figure out the final velocity. So that's the something we care about, right? So we want this, and we know vi. Okay, so the question is, do we know delta p over m? So what's this, right? What's this? So the answer is from momentum impulse theorem, because it says that delta p equals j. Okay, and j is defined as the string's force integral from initial to final time. Okay, so if we know that, then we should be able to do this calculation of the v final, and that integral is the area under the curve. Okay, so let me draw this area, and that's this shaded area. And in a lot of situations, we can actually calculate this area. Okay, suppose we know it's bell shape, and we could have some Gaussian function to imitate this bell shape. So that's just one example. Okay, so Gaussian function, and we can do this integral, right, of the area. Okay, then we can calculate the delta p or j, and then we can figure out the v final. Okay, so that's just the one general discussion of how we can apply this impulse momentum theorem to a process that look like this. Now another process I want to address here is called a collision process. And in such a process, of course, the let's say these two objects collide. Object A collide with object B, and that is called the collision process. Okay, so in the process, of course, the force between the two objects, they changing with time. Okay, so collision also has a variable force, varying force, sorry. Force is a function of time. Not only that, but also it happened quite quickly. So the process, let's call it delta t, the time interval here is in the order of millisecond. So in the order of millisecond, and then it happens very quickly. And we'll see later on that this one is the important condition for neglecting some other forces, some external forces in the process. Okay, so these are the two properties of collision process, and then we're going to say that in such a process, we can apply impulse momentum theorem in the sense that we can neglect this impulse, okay, this net impulse. We can say that it's almost zero, and then we have delta P equals 0, which means P final equals P initial. Okay, and that is called momentum conservation. So in the collision process where two objects collide, it happens very quickly, and then due to that condition, we can say that's momentum conservation. Okay, so I said that the net torque on the object equals 0. This net torque refers to net torque due to external forces. The interaction between A and B does not count as external force. Let's look at one picture here. Now, when they collide, I'm going to draw that collision instant. We have A and B touching each other, and there's a normal force, of course, between them. There's normal force B acting on A, and there's normal force A acting on B. Okay, so these two forces, they're action reactions, and they're equal in magnitude, right? So that's something we already know. But we're going to say that these two forces, they are internal. They're internal forces. So they do not go in the calculation of the net torque. If we say our system is A plus B, okay, so our system is not A or B, it's A and B together, right? They together, right, is called our system. So that will make the normal force between them internal forces. So do not consider them here. Okay, so external forces in this example here. So now let's say they collide on a horizontal surface. On a horizontal surface. Then in order to have this condition, we would say let's say when they collide, there are some frictions, right, acting on them. So the friction force are negligible. So in this case here, I'm going to draw, let's say, when they are colliding, they're still sliding on the surface, right? So that's Fk here acting on A, Fk here acting on B. Okay, so we're going to say these two forces are almost zero. Okay, in the sense that these frictions they're much smaller, much smaller than the normal force. Okay, in that sense. So that's how we can neglect them. Okay, if you think about the collision process, it also happens very quickly. So the impulse, we can further reduce the effect of these two frictions by looking at the impulse they deliver to the system. Okay, so the impulse due to Ka, so approximately Ka delta t, and due to this small scale of the time, that's almost a zero. And similarly for the impulse for B. So that's how we can neglect them. Okay. Now some other situations. Before I talk about other situations, so you may say there's also this normal force on A, normal force on B, and then there's gravity A, gravity B. Okay, so I'm going to say that in this case here, because of the support of the horizontal surface, these two pair of forces, they cancel each other. So if I think about the object A, normal force plus gravity, these two vectors must be zero, right? Because they're in opposite directions. And similarly for B, and that's why their collective contribution to the torque will be zero. So the torque due to, their collective impulse, normal force plus gravity, will be zero. They will cancel out. Okay, so this net impulse here becomes zero. So that's why we can neglect them. Now let's talk about one case where we don't have this cancellation, and then see how we can argue that the collision process conserves the momentum. Okay, so it's a collision in mid-air. Okay, so let's say there's this object A collide with object B in mid-air. Okay, so why can we neglect external forces such as the gravity, MAG, MBG? Okay, so we're in the process of collision. These two forces are still acting on the A and B, right? So also the external. So we should account for that contribution for the impulse. J due to gravity, right, is given by, for the whole system, the total gravity here times delta t. Okay, so that kind of impulse will be delivered to the change of the total momentum of the system. So the system here is A plus B. So think about the total momentum change for both A and B. Okay. Now we're going to use the argument that we talked about in the earlier slide. We're going to talk about this delta t here. Okay, because it happened very quickly. Even if it's in mid-air, this delta t is in the scale of millisecond. Okay. Now the normal force between these two objects, we can say, during the collision, it's much larger than the gravity. So that's why either from the scale of the force, the magnitude of the force, but also the time scale here, right, the delta t scale here, we can say we can neglect them. Okay, so we in the future Can you neglect this impulse due to the gravity? So that's the collision process. Okay, so now I'm going to talk about different types of collision. And then what's the property of these types of collisions? Okay. Now for all collisions, we know their momentum, total momentum, is always conserved. So let's say there's a collision between A and B. Okay. So first property, momentum, total momentum of A and B is always a constant. That is always conserved, right? Momentum is always conserved. Now the second property is the basis of dividing the collision process into different types. Okay, so the second property that I'm going to discuss here is the energy, mechanical energy. So we talk about this mechanical energy in a different chapter. So if you're not familiar about this mechanical energy definition, I would suggest you go there first and then return here to think about the energy description of the collisions. Okay, so the mechanical energy symbol is E, and is defined as K plus U. Okay, so here's mechanical energy. Now K here is called a kinetic energy, and U here is called a potential energy. Okay. All right, so that's kind of like a simple definition of this energy that we're looking at. And kinetic energy is defined as 1/2 mv squared. Okay, so it's related to the mass and the velocity squared of this object. And potential energy here, we're going to just consider the potential energy due to the gravity. Okay, so that's mg times the y position. Okay, so we're going to build a coordinate system: x horizontal, y vertical. And if an object with mass m is at a coordinate of y in such a system, and we regard the y equals 0 level as 0 potential level, then we have mgy as the potential energy of this object. Okay, so that's like a quick definition of various quantities. Okay, so with that definition, the second criteria here that we're going to use to divide the collisions into different processes, different types, is that based on the energy conservation here. Now, if before the collision we call this EI equals final mechanical of the system, then we say this kind of collision is elastic collision. Okay, now if the energy is lost, the part of the energy is lost, so EI is greater than E final. Okay, then I'm going to say this kind of collision is inelastic collision. And inside this inelastic collision, we also have two different categories. One is simply just inelastic, called inelastic, and the other one is called completely inelastic. So what's the difference between these two? Let's look at one example. Let's say there are two objects here colliding. Okay, now after the collision, so that's before, let's call this I state. And after the collision, they stick together. So that's this VA and VB. Now after the collision, they move together with a common velocity. Let's call this VC. Okay, so that's final state. So here is common velocity. Okay, meaning they stick together and then move together, and that is called completely inelastic. That's the definition of this. Okay, now inelastic collision will be after the collision, A maybe go that way, VA final, and B maybe go this way with VB final. Okay, so they have two different velocities. They will separate. Okay, that's called inelastic collision. But nonetheless, they still lose energy. Okay, so in this case here, there's still less final mechanical energy compared to the initial mechanical energy. Now, there's another category of the collision process. In that process, initial energy is less than the final energy. So the mechanical energy of the system increases, right, during the collision process. And these processes are also called explosion. Okay, so what kind of process gives us this? So let's say originally A and B, they're together. They move with some velocity, some common velocity. And then later on they explode. And then they break up into two different pieces. VA final and VB final. That's in the final state. Okay. Now, of course, we don't actually need this VC here. So now let's say there's an object at rest at a location, right? And then it suddenly explodes. That's also our case here. Okay. Now, where do we have this extra energy, right? Where do this energy come from? The energy comes from other types of energy, not mechanical energy, some chemical energy. For example, okay, so in an explosion process, chemical energy becomes the mechanical energy of the system. So there's still energy conservation. It's just that mechanical energy is not conserved. Right? Other type of energy is converted into the mechanical energy. So that's called different types of collisions. Okay, and I hope that helped your conceptual understanding of the collision process. And next time we're going to talk about how to apply momentum conservation to study this collision process. Okay, so again, as I said, that the total momentum of a system is always conserved. Okay, so we don't need to worry about whether we can apply this momentum conservation or not to collision process. In such a process, total momentum is always conserved. Okay, and we don't care about the energy conservation right now. But in some other cases, when we want to do more calculations, then we will talk about the energy. Okay, and we'll see that in the next video. Thanks for watching.